Alright, topic C is about sequences, and then we're going to talk about series later on. So a sequence, it's a list of numbers that follow a number that follows a pattern. Okay. And this may seem like it's confusing, and the notation does look confusing, but we've been doing stuff like this all year. Think about a linear function. We're adding 5 each time. That is a pattern. Our exponential functions, if we're multiplying the previous number by 2, that is also a pattern. So it's things that we've been doing all year, just a different name for it. All right, so a couple different notations we have. We have an, and then we have n. You can kind of think of that as, well, an, that's like our y or f of x, and n is like our x value. So we can kind of relate this back to working with functions. So in our first example, we're going to list the first 5 terms of each sequence. So again, you could think of this as y equals 2x plus 5, and then just plug in the numbers for x, 1, 2, 3, 4, 5, and so on to get your answers. So for the first couple, I'll write them out. So a1, because that's the first term, will equal 2 times 1 plus 5, which is 7. a2, 2 times 2 plus 5, and that will equal 9. a3, 2 times 3 plus 5 equals 11. So you can see we're just adding 2 each time. So a4 would be 13, 11 plus 2, and a5 would be 15. Do 13 plus 2. Alright, now letter B, let's look at that. a1 equals 10 times 2 to the first power. That equals 20. A to the second power, a2, 10 times 2 to the second power. And you type that in the calculator if you need to and get 40. a3, you can type that in the calculator and you get 80. So you can see we're multiplying by 2 each time. So a4 would be 160. a5 would be 320. So again, this is just like an exponential function. It's just written a little bit differently. This one, we have a1 equals 1 squared, which is 1. a2 equals 2 squared, which is 4. a3 equals 3 squared, which is 9. a4 equals 4 squared, which is 16. a5 equals 5 squared, which is 25. So you can see, oh, we're just squaring each number, kind of like y equals x squared. Just another name for it. So I think you'll find that this is not too bad once you understand the notation that goes with it. Alright, there are 2 types of sequences that we're going to talk about. The first one is arithmetic, and that is when we add or subtract the same number each time. Add or subtract the same number each time. So that's like a linear function. You want to think about that as linear. And how that would look on a graph would be a line. with some starting value and then a constant rate of change or slope. We wouldn't really need the line there. The next one is called geometric. And that one you are multiplying or divide by the same number each time. So that was like our exponential functions. So again, for that, you'd have some y-intercept, and then you'd have an exponential function that gets larger and larger. So if you think about it, geometric is your exponential functions, arithmetic is your linear functions. And then there'll be others that are neither, but we're going to focus on these two for now. Alright, let's look at the next page, please. Write the next term, and then write the rule for the nth term of the sequence. Determine whether the sequence is arithmetic, geometric, or neither. So, remember when we were making tables, we always had to go backwards and find out what the y-intercept was. So let's do the same thing. So we have n and we have an. We don't know what the zero term is. We know the first term is 4. 1, 2, 3, 4. So the first term is 4. The next one is 8, 12, 16. So if we look at the values, we're clearly adding 4 to each time. Plus 4, plus 4. So to go backwards, this must be 0. Alright, so the next term, add 4, we're going to get 20. Now the rule. An equals, well, we're going up by 4 each time, so we write 4n. And since our starting value right here was 0, we don't need to write anything. You could write plus 0, but that would just be a little bit annoying to do every time. So we don't need to do that. And is it arithmetic, geometric, or neither? Because we are adding 4 each time, that is arithmetic. So adding something each time, arithmetic. Multiplying by something is geometric, and if there is no pattern like that, then it's neither. Alright, let's look at this. Letter B. So we're going to make a table again. Eventually, you'll get to the point where you won't need to make a table. So n, an, we have 0, 1, 2, 3, 4. So first term's 9, then negative 27, positive 81, negative 243. So I'm looking at what's going on here, and we are multiplying by 3, but also the numbers are changing from positive to negative, and then negative to positive. So our rule is we're multiplying by negative 3 each time. And then if we wanted to find the next one, we would do negative 243 times negative 3 and get positive 729. So now to go backwards, what needs to be here is negative 3 because negative 3 times negative 3 is positive 9. So then our function is a(n) equals negative 3 times negative 3 to the n power. So this looks a little bit different than our exponential functions because we never had a negative number raised to the power when we did exponential functions. But see, we're clearly multiplying by negative 3 each time. So that is why negative 3 is right here. So this negative 3 was our y-intercept, or our starting value, right here. And this negative 3 is our growth rate. From here. Alright, letter C. Again, let's look at this table. We have n and we have a(n). So 0, 1, 2, 3, 1, 2, 3, 4. And we have 1 over 2. Or sorry, whoops, I missed. We have 1 over 1, 1 over 2, 1 over 3, 1 over 4. So you can clearly see that, alright, it's 1 over n. 1 over 1, 1 over 2, 1 over 3, 1 over 4. So the next term should be 1 over 5. But when you look at this, there's no numbers that you can add each time or multiply each time to get the next one. So this is neither. And the rule would be, remember to go find the rule, we got to go back. Well, you can't do 1 over 0. That's undefined. So our rule will be a(n) equals 1 over n, but n cannot equal 0. Because that would give us an undefined answer. Oh, it looks like for letter B, I forgot to give us, tell us if it's arithmetic, geometric, or neither. Because we're multiplying by the same thing each time, it is geometric. Okay, letter D. Let's make a table. And we have n, a(n), 0, 1, 2, 3, 4. And our y values, 1, 1/8, 1 over 27, 1 over 64. So what I've noticed is that, alright, 4 to the third power is 64. 3 to the third power is 27. 2 to the third power is 8. Well, 1 to the third power is 1, and 1 over 1 would be 1. So this one would actually be 1 over 0 to the third power, and that'd be undefined. So then our next term should be 1 over 5 to the third, or 1 over 125. 1 over 125. Then the rule, that would be a(n) equals 1 over n to the third power, but just like the last one, n cannot equal 0. And this is not arithmetic, it's not geometric, it's neither, because we're not adding or subtracting the same value each time. That's what makes it neither. Alright, then let's look at example number 3. Write a rule for the nth term of the sequence. So let's make a table out of these points. N, a(n), we have 0, 1, 2, 3, 4. We have 5 in this one. And then our y values, 48, 24, 12, 6, 3. So we got to see what is happening each time. We're multiplying by 2 times 2 times 2 times 2. So that's my growth rate is 2. So then what comes before this, we would have to do 3 divided by 2, which is just 3 over 2. Let's not complicate things. We can leave it as a fraction. That makes 3 over 2 our y-intercept, and our growth rate is 2. So we would have an equals 3 over 2 times 2 to the nth power. Okay, so you will probably find these a little bit easier if you've done well with writing equations of exponential and linear functions from a table. So you can start your homework, and good luck.